So our next speaker I'd like to introduce is Kris Ardis, the Executive Director of Micro Security and Software.
Thank you very much. I'm trying to get sharing here. Can you let me know if you can see my presentation here?
Yes, I can see it.
Great. Okay. Thank you for the invitation to chat with everyone today. So I'm Kris Ardis. I'm based in Dallas with Maxim integrated, and I'm in our microcontroller group. And I want to talk today about a new technology that we brought to market to accelerate edge inferences, particularly for embedded kinds of devices, and also talk about some of the challenges that we're seeing in the industry to actually making that happen. This deck might feel a little bit markety-ish. I'll try to skip some more of the markety things. But with all the excitement that we see in the market today for AI and bringing the ability to machines to let them see and hear, we have noticed a gap, and I think this is a theme that we see with groups like TinyML as well, is the need to be able to run and bring machine learning technology to smaller devices that are constrained. We see a lot of the AI and interesting things happening today in the unconstrained devices on the left, like self-driving cars. But with the devices on the right, we rarely see things beyond simple wake words and very small networks. And we don't see in deeply embedded equipment the ability for those devices to see and actually implement vision-based inferencing. And so that's really the gap that we've tried to address. And the reason for that is the same. It's both a blessing and a curse is the convolutional neural network, which does such a good job of processing images and making inferences on images, and brings us a lot of the things we all associate with AI in our heads today. But the downside of that is the computationally expensive nature of the CNN and all the multiplications that have to go into it lends itself to bigger processors to do these more interesting jobs. And that really prevents this type of technology from being brought to the edge, from being at a cost point or a power point, or even a size that is capable of being in, for example, a wristwatch or a small battery powered camera or things like that. We've talked to a number of customers who have visions for what they would do if they could bring vision to the embedded equipment. We highlight a few things here. We see lots of camera folks interested in counting people for HVAC controls, for Face ID, for authenticating people to a door or something like that. The robot vacuum there, it's a personal pet peeve of our system architect. We certainly see value, and I would spend a few more dollars if my robot vacuum didn't get in a fight with things. And we see interest in even more advanced audio applications too. And so we think that there's a big universe of possibilities when you can let smaller embedded equipment see and hear much more like us. So I think the challenges from where the market is today to get there are really these four pretty standard trade-offs that need to be made to optimize energy, to optimize latency, and the size and the cost of a solution to bring some of that vision-based AI to embedded equipment. So let me talk a little bit about the part that we've introduced to the market and what it can do, and then I'll talk some more about the challenges that we see. So a device that we've recently introduced to the market, it's a microcontroller that actually has a dedicated CNN accelerator that actually consumes about half of our chip. In this architecture, the micros are actually not involved in the CNN inferencing, as you see in a lot of other implementations. The microcontrollers, they are there for system control, and they are there for getting data from the outside world to that CNN accelerator. The accelerator is otherwise self-contained. Once the microcontroller tells it that its data is loaded and tells it to go, the CNN runs autonomously on its own. We've gone to great lengths to try to minimize the data movement to really optimize the energy spend in this accelerator. One of the limitations that brings, and I'll get more to that in a second, is since we are self-contained in hardware and we intentionally do not access external memory, that limits the size of the networks that can actually be implemented in this device. You can see there, there's 432 kilobytes of weight memory. With down to 1-bit weights, that's up to 3.5 million weights can theoretically be implemented in the device. So the accelerator, it's our own architecture meant to maximize parallelism and optimize the energy spend. And it is highly optimized for convolutional neural networks. Just a couple of examples of what it can do. We have a demo running the keyword spotting on the Google data set. That takes about 30% of the resources in the chip. And then we also have a Face ID demo that takes about 40% the resources of the chip. Executes in about 2 milliseconds. We actually spend far more time getting the data from the camera than we do doing the actual inference of the Face ID. And so you see that there's certainly a lot more that these chips could do, which actually gets to one of the challenges, is trying to take larger and larger networks and shrink them down to a size that can run in our devices. So just a couple notes on the compelling nature of this technology. We've running the exact same neural network on one of our low power Cortex M4F microcontrollers that actually goes into wearable devices, and then comparing that to our hardware accelerator, we're seeing several hundred times lower energy spend on an inference, and a couple hundred times faster inference compared to that micro that runs at about 100 megahertz. And so what we think that really enables is not just kind of the standard trade-off of, hey, I can make my battery smaller, I can make my device run longer, but you can actually bring applications that weren't really envisioned for embedded devices to those devices. Things like any kind of device that can see, maybe get paired to a person based on who it's looking at, things like that. And because this is an embedded, meant to be an embedded device, we also think we have a good position on size and cost as well. So I want to talk about some of the challenges that we've discovered bringing this chip to the market. While we're pretty proud of the job here that it optimizes the energy spend in our hardware for machine learning inferences, we think that there's definitely challenges in neural network architectures that can solve vision problems in an efficient manner. There's some different edge hardware approaches listed here, things like GPUs and high-end processors that are great because they can run any neural network quickly. They also have extremely high cost and energy consumption. And they can do great things. They can run cars, and that's not really our target. But there's definitely a different universe at the edge and in IoT kinds of devices where they can't afford that cost and that level of energy consumption. Things like microprocessor, microcontrollers, we think the power and the latency there, when you start to get into vision applications, starts to really limit the adoption of those types of devices. And so our approach is energy optimization, but with the limitation on the network capabilities I mentioned before. So these limitations, and actually the slide should more appropriately say addressing these edge limitations, that it's not just something that I think is interesting for Maxim hardware. I think it's something that's interesting for the industry, because the better job that we can do delivering faster networks for the edge and lower power networks for the edge helps any embedded device trying to implement AI. We see faster networks as important, especially for safety applications. Avoidance, drones trying to avoid each other or obstacles, for getting a quick answer on, for example, who's at the door without having to go to the cloud are all pretty important things for edge devices to accomplish. And then lower power networks at the edge are it's critical to get there for some of these unimagined use cases, vision and hearing where it wasn't really possible before. And we see that as one of the big obstacles to really increasing AI adoption in the IoT, and actually a big opportunity for university engagement as well. So some of the things we think are needed to achieve that. One is more clever edge network architectures. We found a few partners who are trying to do things like object detection at very small size. But certainly one of the things we run into quite often is people trying to put, networks that are, many tens of megabytes in size, in a small embedded device. And they have a hard time crossing that gap to really achieve an embedded low power solution. We think that, university engagement is also pretty important. We realize a lot of people playing with this technology today are probably doing it on these big processors that have very high power consumption, but also great performance. But I think there's an opportunity there to also teach about limitations and constraints of embedded devices and clever ways that that network architectures can be implemented in embedded devices. And then kind of the holy grail of neural architecture search, trying to find the perfect size network given a set of restrictions, and a set of goals, and a data set. So certainly that type of a solution would benefit everyone, not just the embedded people, but anyone running larger networks as well. So just one last slide just to talk about what we've got. This part that we've introduced, we are actively engaging with partners trying to find these smaller networks and trying to implement more interesting vision problems at the edge. We support standard tools. We have plenty of development hardware available. So we're definitely excited about trying to engage with industry partners and academia partners to really enable interesting AI at the edge. And that's it.
Very much, Kris. That was really interesting. Are there any questions? I'm sorry, I didn't mean to cut you off if you weren't quite done. I jumped the gun there.
No, that's it. I'm also joined by our system architect, Robert Muxel. So for any type of deep architectural questions. Okay.
Are there any questions on that?
I wanted to ask one question. When will this Max 78,000 architecture be out and possibly made available to universities and other institutions?
It's available now.
It's available now.
Yeah, we released it about a month ago. We did a press release last week, so we're ready to go.
Okay.
Fabulous. Now I do have one quick question. It has the built-in CNN Accelerator. Now, is it? You may have mentioned this. I may have missed it. Is this really limited to image processing applications? Or can that CNN Accelerator be a little bit generalized to some other applications such as LSTMs or recurrent neural networks?
Yeah, so I'll say maybe I can answer generally, and Robert, you can speak more specifically. There's a set of operators that are supported in the CNN Accelerator, and we've really tried to focus on CNNs, which kind of lends itself a little bit more to vision. We're certainly doing audio applications with those CNNs as well. Okay. And nothing to prevent that. Robert, maybe you can speak more specifically.
Yeah, we always talk about vision just because people can understand it better. It's to demonstrate, but there's nothing. It's general purpose. It's like a microcontroller of accelerators. You can put anything in there and get anything, but as long as it's supported by the operators that are implemented in hardware.
Okay, thank you.